All right, so we're working on problem number 4. This one gives us the formula for the spring force, and notice that it is not a typical Hooke's law equation. So what we are asked to do is solve for the constant A, or in the diagram it says alpha. So what we're going to do is I'm going to look at the equation and try to turn it into a line. So y equals mx plus b is my line. I want alpha to be my A. And so my y value would be force, and my x variable would be negative square root of x. I don't have a b value, so that's going to be 0. Now, what I notice, though, when I look at my graph, is that the graph does not have any negatives. It starts at 0 and only gives us the first quadrant, which is the positive side of the axis. So I'm going to get rid of the negative and just solve for alpha, and then I can turn the alpha into a negative later. But the x and y axis would be force in newtons and the square root of x in meters to the 1/2, or square root meters. So what I'm going to do here is I'm going to take my table and I'm going to take the square root of the compression. That's the square root of these values right here. And then I'm going to fill them in. I'm going to plot them. And again, this is all eyeballing it, and your estimation might be slightly different, but as long as you kind of go through the same process, you'll get the credit for it. So this is the data that I got for taking the square root of the compression values, and I have plotted the compression values and force on the force compression graph, and I draw a line of best fit. You can see the dots where the data points are, and then you can see the X's where I've decided to use my points for my slope that are on the line but not data points. And again, even though it goes through 0, 0, please avoid using 0, 0 as a point for your slope for part B. So the points I chose in the previous graph were 0.333 and 8 and 0.1674. And to get alpha, I take the slope, which is y2 minus y1 over x2 minus x1. My second point was this one. My first point was this one. So I'm going to start with 8 minus 4 all over 333 minus 0.167. And I end up with 16 Newton square root meters, or meters to the negative 1. So that is my unit because of choosing square root of x as my x value. Now, this does not match the answer from the answer key. I think the answer from the answer key was 25. But like I said, everyone's going to get a different estimation as long as you did choose points that are not data points and that are on your line of best fit, and as long as the line of best fit is fairly toward the center of your dots, where you've got a few dots above and a few dots below, evenly scattered throughout, then you should be fine. If you have any questions, just come up and ask during tutorial or class. So this is part B. I'm gonna go on to part C. It says develop an expression for the potential energy that can be stored in the spring. Well, the potential energy, and we're also given the force equation, can be put together in the du dx is equal to negative F equation. Remember, they are opposites of each other. And then I have an equation for F. So I'm going to plug in that equation, which is negative alpha to the x to the 1/2. And then I am going to take my dx and bring it to this side so that my x's are together. So from there, I've got du, not dx, is equal to negative alpha x to the 1/2 dx. And I left a little space there because I know that I have a du on the left, du on the dx on the right, and I will take the integral of both sides. The integral of du is just u. The negative alpha is just a constant. I'm going to keep it as a fraction, and I'm going to do x to the 1/2 plus 1, which is x to the 3/2. And then I'm going to divide that by 3/2, which is really multiplying by the reciprocal. And I get u is equal to 2 alpha x to the 3/2 over 3. Okay, so for this scenario, we've got the spring put into a spring gun and it is launched off of a horizontal edge. This is 0.75 meters. This is the spring gun, and then this is the path of the dart. We want to calculate the range here, but we would need to figure out the velocity we would need to figure out the velocity in which the object is launched to get the time it takes to land in the ground. Usually we want to use the y component for that, which is the case here, and then we can calculate the range using that same time value. So I'm going to start with the fact that we have a spring compressed. So initially we have some spring energy and some gravitational energy. So US plus UG. And then that turns into once the spring is launched, it's going to turn into kinetic energy and the same amount of gravitational energy, because as soon as the dart is launched, it is no higher or no lower than it was in the spring. So I'm going to set these equal to each other. I know that the gravitational height is going to be the same for both, so that leaves me with the spring energy equal to the kinetic energy. And at that point, I have 1.8 joules for the spring, and then I have mgh for, not mgh, the mgh canceled out, it's the 1/2 mv squared. Okay, so I'm gonna find the velocity for the object to launch, and that's gonna give me the horizontal velocity. Actually, that's perfect because we need the horizontal range. So I'm gonna get 1.8 joules is equal to 1/2 times a mass of 1/2 velocity squared. 1/2 times 1/2 is 1/4. So if I multiply 4 to the 1.8, I get velocity squared. And then when I take the square root of that, I get the velocity is equal to 2.7 meters per second. And that gives me this Vx, which is perfect because if I'm to calculate the range, I want that velocity component. So from there, I am going to use range, or x, is equal to x naught, which is 0, plus v naught, that's going to be my 2.7, times t, no acceleration, so you can cancel out the 1/2 at squared, but the problem is I need t. So to get t, I need to work with the y component first. So I'm going to start with y naught is equal to 0.75. I'm going to have y is equal to 0. V naught is equal to 0. Acceleration is equal to negative 9.8. I don't know the final velocity and I don't know the time. So in this scenario, I'm going to use y equals y naught plus v naught t, but that is equal to 0, plus 1/2 a t squared. And I get 0 is equal to 0.75 plus 1/2 times negative 9.8. That gives me a negative 4.9 t squared. And I am going to subtract the 0.75 over and divide the negative 4.9 to get t squared. And when I simplify that out, I end up with about 0.39 seconds. That is the value I'm going to plug in here. And so R is equal to 2.7 times 0, sorry, that should be a comma, 0.39, and I end up with 1.05 meters.